minus 1 plus 1. Okay, and this is the formula. You have to very carefully remind that this is the formula, that is x to the power 2 to the power m minus 1 plus 1. Okay, so this is the irreducible polynomial, or the properties of the irreducible polynomial. That means I'm again repeating that any polynomials, if it does not possess any factor polynomials of degree which is lower than the degree of the main polynomial, then it is called the irreducible polynomial. Like 1 plus x squared, it does not possess the factor of degree 1. So that's why this is called the irreducible polynomial. Okay. In case of x to the power 7 plus 1, it possesses a factor polynomial of degree which is less than 7. That is 1 plus x cubed is a factor polynomial of degree 3 which is less than 7. So that's why 1 plus x cubed is a irreducible polynomial of x to the power 7 plus 1. Okay. So this is the concept of irreducible polynomial, and also the factorization of the polynomials. Okay, the factorization of the polynomials in GF field, that means Galois field. So these are the factors. 1 plus x cubed is a factor of x to the power 7 plus 1. So now we will see that how this x to the power 7 plus 1 came from. Okay. So for this, we have to consider new thing. Let me just use it. Okay. Now we will consider this PDF. So from this PDF, what is written here, that, so first of all, from the previous lecture, I've told you that any polynomial equation does possess, that to possess its roots, and here it is written that conjugacy class and the minimal polynomials. Okay. Minimal polynomials. So okay, we will come to this later. So first you have understood that this is the concept of irreducible polynomial and the factorization condition of the irreducible polynomial, what is the factors and the significance of the factors. Okay, so now we will go to previous BCH code chapter. Okay, so from this, so we have seen that from the appendix B, so this is described and clarified appendix B. So as an example, the Hamming code like 7,4 introduced in chapter 2 and 3 is analyzed here. So in order to see which of the roots of its generator polynomial, like gx. Okay, so I've told you that gx is a polynomial equation, so it too possesses also the roots, and since any code vector, carefully go through this, since any code vector is generated by multiplying the given message vector by the generator polynomial in case of cyclic code. Okay, We know that any code vector Cx will be generated by multiplying mx and the gx. So any code vector seen as a code polynomial, and that code vector will be also in terms of code polynomial, will have at least the same roots as this generator polynomial. Okay. So in case of cyclic code, the code vector is being generated by multiplying the generator polynomial with the message polynomial. So those which are the roots of the generator polynomial, that will be also the roots of the code polynomial, right? Will have at least the same roots as this generator polynomial. So this means as we have multiplied with gx, that means generator polynomial with the message polynomials, and we are generating the code polynomial. So the roots of the generator polynomial will be same as the code polynomials. Okay, at least same. Okay, at least the same roots. So from this concept, we can say that this allows us to construct a system of the syndrome equation. Why? As the roots of the code polynomials are known. Roots of the code polynomials are known. That means in case of cyclic code, when we are receiving a code, suppose we are receiving any code, right? And we know already what is the roots, what are the roots of the generated code, what are the roots of the generated code polynomials, and we are receiving a different code polynomials. Okay, so as we know that what are the roots of the generated code polynomials, so we can compare the roots of the received code polynomials with our known roots of the generated polynomial. Okay, so in this way we can detect or we can correct that how many number of error presented in the received polynomial. Are you understood that we are generating the code polynomial by multiplying the generator polynomial with the message polynomial? Okay, so the generated code polynomial, the roots of the generated code polynomial will be almost same as the roots of the generator matrix or generator matrix, that means generator polynomial, right? So when a code is being transmitted, we already know that the roots of the generated code. Then when we receive a different code and when we transmit it to the received code polynomial, or we represent it in a polynomial equation, so and then we will calculate its roots. If those received roots, that means the roots of the received code polynomial, is not matching with our known roots, which we are already known, okay, then we can say that there is error. Okay, so this is the syndrome technique. So this technique basically helpful in case of error correction and detection technique. Okay, so this is basically the significance of calculating the roots of the generator polynomials. And now we will go to the significance of the minimal polynomials. So this is the basic intention. Okay, so in this way we will correct and detect the error bits of the received code by comparing the roots of the received code polynomials and the known generated code polynomials.